In this video, we will look at how to go from position to velocity and also in the reverse order from velocity to position. We have already seen that in one-dimensional motion, Vx, that is the x component of the velocity, is the derivative of x with respect to time, dx over dt. So if we are given an x versus t graph, then the velocity component Vx is just the slope of the x versus t graph. Here, we've been given an x versus t graph, and the question asks us which of the four following graphs most closely represents the velocity of this particle. Here are our four options. So, what do we need to look at? Well, we need to go back to the position versus time graph and look at how its slope changes. We see that initially, the slope of the graph is 0, it's a flat line. It then smoothly changes into a positive slope. So it goes from 0 to positive, so it must be increasing. And then after that, it goes from positive back to 0. So we need a graph that goes from 0 to positive to 0. We see that this graph starts negative, not 0. This graph starts at 0 and then goes positive, but then goes negative and then goes 0. This one starts negative, but this one is right. It starts at 0, goes positive, and then goes back to 0. So B is the answer. In the second example, we are again given an x versus t graph, and this time we are asked to sketch the velocity graph that corresponds to this x versus t graph. When given a question like this, it is always a good idea to mark the points where some kind of transition or change happens. For example, we see that at this point, the slope goes from 0 to something positive. We see that at this point, the graph reaches a maximum. At this point, the graph reaches 0. At this point, the graph reaches a minimum. And at this point, the slope changes back to 0 again. So let's mark these transition points using drop lines so that when we draw the v versus t graph, we can make sure the transitions happen at the right spot. Right, these are the drop lines. Whenever you are given a question where you are given one graph and asked to draw some corresponding other graph, like here, where you're given the x versus t graph and asked to draw the v versus t graph corresponding to it, always draw the drop lines first. Alright, now we start drawing. In this first part, we see that the slope is 0, and so the velocity stays 0. In this next portion, we see that the slope has gone from being 0 to suddenly going to a positive value. After staying at that positive value for a while, it smoothly goes to 0. And so that is what we see over here. Here there was a sudden transition in the slope. Here there is a sudden transition in the value of the velocity. And the velocity, after staying at a constant positive value for a while, smoothly goes to 0. In this next portion, we see that the slope goes from 0 to a steep negative slope and then back to 0. Notice that this negative slope here is much steeper than the positive slope here. And so that is what we see here. The value of the velocity goes from 0 to a negative value and back to 0. We see that the negative value is much more negative than the positive value here. And we see that the minimum negative value occurs a little bit before 3.5 seconds. In this next portion, we see that the slope of the x versus t graph goes from 0 to a constant positive value. And so that is what we see over here, smoothly going from 0 to a constant positive value. And in this last portion, we see that a little after 6 seconds, the slope of x versus t goes from a positive value, suddenly jumping to 0. And so that is the transition we see over here. The velocity jumps down from positive value down to 0 and stays there. One other final check we can do is to keep in mind something we will see in a bit more detail later, which is that the area under the curve for a velocity versus time graph gives you the displacement. Here, the final displacement is 0 because the particle starts at 0 and ends at 0. This tells us that the total area under the curve for a velocity versus time graph, in this case, should also be 0. And we can see, yes, this positive area and this positive area are roughly cancelled out by this negative area. That serves as a good check on our picture. And so, this v versus t graph is roughly the one corresponding to this x versus t graph. Here are a few tips to keep in mind when drawing one graph based on another. We know that when we take the derivative of t to the n with respect to t, we get n times t to the n minus 1. In other words, you had t to the n, but now you only have t to the n minus 1. In other words, you have lost one power. So, if you take the derivative of a quadratic function, like t squared, it becomes linear. Here's a general example. Here b, c, and h are just constants, and we can see when we take the derivative of bt squared, we get 2bt. When we take the derivative of ct, we just get c, and h has gone away, because the derivative of a constant is 0. So it has gone from a quadratic function to a linear function. And similarly, if you take the derivative of a linear function, say bt plus k, then you just get a constant. What relevance does this have to the graphs? Let's take a look at this graph. Again, we are given an x versus t graph, and we are asked to draw the corresponding v versus t graph. We notice that it can be split up into regions where the graph is linear, regions where the graph is quadratic, this is a parabola, and again, regions where the graph is linear. So we can see that when we take the derivative and find the velocity, this region where the graph is linear, after taking the derivative, will correspond to a constant. This region where the graph is parabolic or quadratic, after taking a derivative, will correspond to a linear region. And again, this region where the graph is linear, after taking a derivative, will correspond to a constant. Once again, we draw the drop lines. And now we try drawing the v versus t graph. And so, in this first region, x is a linear function of t, and so v will be a constant. And we can see that the slope here is positive and constant, and so the value here is positive and constant. In this next region, we notice that the x versus t graph is parabolic, that is, it's quadratic, and so the derivative will be linear. However, will it be linear like this, or will it be linear like this? We look at what happens to the slope. We see that the slope starts out negative, goes to 0, and then goes positive. If we try drawing a line like this, we see that the value starts out positive, goes to 0, and goes negative, which is not what we want. Negative slope, 0, positive slope. And so the line that we want must go negative value, 0, positive value. And so we have straight line going negative to 0 to positive. And in this region, we see that x versus t is linear. And so that means the corresponding v versus t will be a constant. And we see that the slope is negative, and so it will be a negative constant. And this is the negative constant. And so this v versus t graph is what corresponds to this x versus t graph. The graph for v versus t does not need to be continuous, even if x versus t graph is continuous. However, notice that these discontinuities, these jumps, correspond to where there are kinks or sudden changes in slope in the x versus t graph. Of course, sometimes instead of a graph, you are given an equation. For example, you might be asked, if the position of a particle is given by this function, x given as a function of t, then when is the velocity 0? Pause the video and try and solve this by yourself, using paper and pencil, or using a calculator. The next slide will show the answer. We're moving to the next slide. We were given position as a function of time. We know that velocity is the time derivative of position, in other words, dx over dt. And so we take the derivative with respect to time of 2t cubed minus t squared minus 4t plus 7. Taking the derivative of 2t cubed gives us 6t squared. Taking the derivative of t squared gives us 2t. Taking the derivative of 4t gives us 4. And taking the derivative of 7 gives us 0. And of course, we keep the appropriate signs. We are asked for when the velocity is 0, and so we set this polynomial to 0. We notice that there's a common factor of 2, so we can pull that out. And so asking when this is 0 is the same as asking when this is 0. We can now use either the formula for the roots of a quadratic equation, or we can factor, and in either way, we find that the roots of the equation are t equals 1 second and t equals minus 2 over 3 seconds. Now, what does it mean when the time is negative? It simply means a time before the time that you call 0. Sometimes this is ruled out in problems. For example, if at t equals 0 you started throwing a stone, then any answer you get which was negative corresponds to a time before you threw the stone and would not be physical. But in a question like this, where no information is given about anything special happening at t equals 0, the negative answer is also a possibility. And so both of these are, at least at the moment, valid answers for when the velocity is 0. So far we have looked at going from position to velocity using the derivative. How do we undo this? We rearrange the equation and then integrate. Here we are integrating with respect to t. We know this because of the dt. Here we are integrating with respect to x. So on this side, the limits of the integral must be times. Here, the limits of the integral must be positions. So we have integral from t0 to t1 of v dt, where v is in general a function of time, is equal to integral from x0 to x1 of dx. This side is easy to evaluate. Integral of dx is just x, and we evaluate it at x1 and x0. On this side, once again, we remember that v is in general a function of time, and unless we are given that particular function of time, we cannot evaluate this side. And so we get integral of v dt from t0 to t1 is the change in position, x1 minus x0. But change in position, we know, is called displacement. Just like the derivative corresponds to the slope of a graph, the integral corresponds to the area under the curve. And so what this is telling us is that the area under the curve is equal to the change in position. However, area under which curve? Again, it's just hidden in the expression. Since we are integrating v dt, it must be a v versus t graph. So the area under the curve for a velocity versus time graph gives the displacement from the starting position. Here's a graphical example. We are given a v versus t graph, and then we start finding the area. However, an area needs to be bounded. So here the bounds are the curve, the blue line, and this, the zero line. If the curve is above the zero line, then this area counts as positive. This is a positive area and corresponds to a positive displacement. Here, the blue line is below the zero line. And so this is still area which is between the zero line and the curve, but this counts as negative area. And here, once again, we have positive area. The sum of all these is the total area under the curve, and that will give us the total displacement. So here's a question. Is the displacement between t equals 1 and t equals 6 positive, negative, or 0? And how much is it? The first part is easily answered. We can see that there is clearly more negative area than there is positive area, and so the total displacement will be negative. How do we calculate the area? This shape is a triangle. It is a triangle with base 1 and height 1. Using the formula area of a triangle is equal to 1/2 base times height, we see that this area is 1/2 times 1 times 1, or just 1/2. Similarly, this area is again 1/2 times 1 times 1, which is 1/2. However, what are the units? Well, we are multiplying a base of 1 second by a height of 1 meter per second. Multiplying 1 meter per second by 1 second gives us a meter. So this area is 1/2 meter. This area is 1/2 meter. What about this area? Here we see that the base is 3 seconds, but the height is -3 meters per second. And so the area, using this formula, is 1/2 times 3 seconds times -3 meters per second. This is -9/2 meters. And so this area corresponds to -4.5 meters. And so the total displacement is 1/2 minus 4.5 plus 1/2 meters, which is -3.5 meters. And that is the total displacement between t equals 1 and t equals 6 seconds. Here is a non-graphical example. If the velocity of a particle is given by v of t is 4t plus 7, and if the position at t equals 0 is x at t equals 0 is 6 meters, what is x at t equals 2? Pause the video and try and solve this by yourself. The next slide will provide the answer. Moving to the next slide. This question can be solved either graphically or by integration. If you want to solve it graphically, draw a v versus t graph using the equation 4t plus 7, and then find the area under the curve between t equals 0 and t equals 2. This area can be split into a triangle and a rectangle, and so it's not too hard to find. Once you have found that area under the curve, that is the displacement. Displacement, remember, is change from initial position to final position. And so to find the final position, you also need the initial position, but that is given to us in the question. So initial position plus displacement will give us the final position. Here I present how to solve this using integration. We are given v of t, which is dx over dt, is 4t plus 7. We rearrange this, and so we get integral dx is integral with respect to time of 4t plus 7. On this side, the integral gives us x final minus x initial. On this side, the integral gives us 4 times t squared over 2 plus 7t, evaluated at t final and t initial. Since we are doing a definite integral between definite limits, we don't need to add constant. We set t initial is equal to 0 and t final is equal to 2 seconds. So we have x at 2 seconds minus x at 0 seconds is equal to this evaluated at 2 and 0, which gives us 22. But we are solving for x at 2 seconds. So we move the x equals 0 to the other side, and we have x at 2 seconds is x at 0 plus 22, which is 28 meters. An important comment is about a common mistake. The common mistake is often to forget to account for the initial position. Remember that the integral of v dt doesn't give you the position, it gives you the change in position. And so you still need the initial position if you want to find the final position. In this question, we are given a velocity versus time graph and asked to find the corresponding position versus time graph. Is it this, C? Is it this, D? Could it be either of them? Or is it definitely neither of them? Pause the video, take a moment, and try and decide for yourself. The next slide shows the answer. First, we note that the value of the velocity is a constant 2 meters per second, positive, and so we want an x versus t graph with a constant positive slope of 2 meters per second. Please note that the slope has units attached to it, and the units are simply given by rise over run, which in this case is meters over seconds. But if we check, we see that both these graphs have slopes of positive 2 meters per second. They only differ in the starting point. This starts at x equals negative 3 meters, and this starts at x equals 0 meters. Without being given further additional information, we cannot choose between them. And so either of these graphs, or possibly some other, could be the right answer. But both of these are definitely possibilities. This highlights an important point, which is when you integrate, you need the integration constant. Or in other words, when you're going one step up the integration ladder, either from acceleration to velocity or from velocity to position, you need to know the initial information, in this case, the initial position. For the next few slides, we will look at several examples where we are given the velocity versus time graph and we are asked to sketch the corresponding x versus t graph. In these examples, we are explicitly told that we can assume that the initial position x at t equals 0 is 0. So all these graphs will start at the origin. Here's our first example. The velocity is some constant positive value. What is the corresponding x versus t graph? In this case, there are no transitions, so we do not need to draw any drop lines. We are told that the initial point at t equals 0 is x equals 0, and so we draw a line starting from there. It's a straight line with a constant slope. Here's our next example. This time, the velocity changes linearly, and it has a constant positive slope. Since we are going up the integration ladder, a linear v versus t graph corresponds to a quadratic x versus t graph. So our x versus t graph will look parabolic. However, does it look like this, or does it look like this? There are a couple of different ways to think about it. The first and simplest is to look at the value of the velocity and see what that tells us about the value of the slope in the x versus t graph. We see that the velocity starts at 0 and grows more and more positive. So that means the x versus t graph must initially have a slope of 0 and then turn positive and get more and more positive. If we look at a curve with this shape, we see that it starts steep and goes to 0. But a curve with this shape starts with a slope close to 0 and then gets steeper. The other way to think about it is to look at the area under the curve. We know that the area under the curve for a velocity versus t graph gives us the displacement, and the initial position is x equals 0. We see that the area continuously grows positive, but initially there's only a little bit of area being added, and later on there's a lot of area being added. This tells us that the x versus t graph starts out small and then gets bigger. So initially the area added is small and then gets larger. Once again, there aren't really any transitions here. Beyond this point, the graph simply goes off the page. And so we draw the corresponding x versus t graph. This parabola has what we said before, the right shape. We can see, now that we have drawn it, that the slope starts 0 and then rapidly grows more positive. And thus that corresponds to the behavior of the value of the velocity over here. It starts at 0 and then gets more and more positive. Again, remember, this curve is quadratic in t. It is parabolic. It is not what we call an exponential curve. Here is our next example. Once again, we are given velocity versus time, and we are asked to sketch x versus t, assuming that at t equals 0, x is 0. Here there is a transition at t equals 3 seconds, so we draw a drop line. Pause the video, take a moment, and try and sketch for yourself what the x versus t graph will look like. We now proceed to discuss the solution. We first notice that this part of the graph is linear. The velocity is positive but going to 0. We know that when integrating a linear function, we will get a quadratic function. And so the x versus t graph for this part will be parabolic. Once again, the question is, does the graph look like this or like this? We see in this case that the velocity starts out at a large positive value and decreases to 0. And so the slope in the x versus t graph must start out with a large positive slope and then decrease to 0. That corresponds to this kind of parabola. Beyond this point, beyond 3 seconds, we see that the velocity is 0. But if the velocity is 0, that means that the position is not changing. And so the position will remain constant. And so we see that the position remains at a constant value. This is the x versus t graph that corresponds to this velocity versus time graph. Here is the next example. Once again, we see that there are some transitions. This point where the velocity reaches 0, this point where there is a sudden change, this point where again the velocity reaches 0. We draw the drop lines. Pause the video, take a moment, and try to draw the corresponding x versus t graph. Take another moment to think of the solution yourself. We will now discuss the solution. We see that in this first part, the velocity is negative but heading to 0. And it is a linear graph, so we know that the corresponding x versus t graph will be quadratic. We also notice that the area under the curve is negative. So we need an x versus t graph which is quadratic, where the displacement is negative, and which starts with a steep negative slope but then goes to 0 slope. We see that this is the curve we want. It starts with a steep negative slope but goes to 0 slope. The displacement is negative, decreasing from 0, which corresponds to the area under the curve being negative. In this second portion, we see that the velocity goes from being 0 to being positive. Again, the graph is linear, and so the graph in x versus t will be quadratic. It will start with a 0 slope and then become a steep positive slope. However, we notice that this positive area under the curve is a little less than this negative area under the curve. If they had been equal, then those two areas would have cancelled out and the x versus t graph would have returned to its starting point. Since they are not equal, however, this means that the final total area under the curve here is negative, which means that the final position at the end of 3.5 seconds should be negative. This is roughly the shape we are looking for. In this third segment, the velocity starts positive and changes linearly back down to 0. So we need an x versus t graph which is quadratic, which starts with a large positive slope and then reaches 0. We see that this is roughly what we want. Large positive slope, but then tending to 0. And in this final portion, the velocity goes from 0 to a negative value. And we see that this quadratic curve over here is roughly what we want. The slope is 0, but then goes negative. And so, roughly, this is the x versus t graph corresponding to this v versus t graph. Here is another example. Once again, we notice that there's a transition, this time at t equals 2 seconds, and so we draw a drop line. Pause the video here, take a few moments, and try and draw the corresponding x versus t graph, assuming that at t equals 0, x is 0. We will now discuss the solution. In this first part, the v versus t graph is linear, which means the x versus t graph will be quadratic. We notice that it starts with a large negative value and changes to a smaller negative value. And so we see that we start with a large negative slope and then turn to a slightly less negative slope. In this next portion, the value of v is a constant negative number, which means that the x versus t graph will be a linear graph with a constant negative slope. Since the v versus t graph is continuous, we see that the x versus t graph will basically continue with the same slope. And so we see that having achieved a certain negative value, the velocity stays there, and having achieved a certain negative slope, the x versus t graph continues with that negative slope. This is the end of this video. I'll see you in the next.